So, now what we see, periodogram provides a very good estimate. We can replace the classical definition of PSD with periodogram, and if we have sufficient amount of data, it will go towards the ideality, that is, it will give us the exact energy at a particular frequency of our choice, and when we are having finite amount of data, which is the case, in that case we will get actually a band pass version of that PSD, the actual PSD. That means, the energy around that particular frequency given by a band pass filter output, which is quite reasonable. So, now we try to find out more properties of periodogram. So, if we have enough amount of data, say n tends to infinity, then we expect the periodogram is going towards that ideal PSD, that Pxx f. Okay. And to create the difference, two things we have done, that we have used the suffix here for periodogram PRE, and because we are computing it, we are getting just an estimate out of the given data. So, we have used this hat. Okay. So, these two things we have done, and then we can get it, that is happening towards, actually merging towards the ideal value of periodogram, which seems to be almost there after the previous result. We can say that, in it other words, that it is a consistent estimator of PSD. Okay. Now, to be consistent, two things actually we need to satisfy. The estimator mean should converge to the true PSD. The estimator mean converges to the true PSD, that is 1 as n tends to infinity. That means, the bias should be 0 and the variance also should tend to 0, because it is an estimator, it can have some small error which can be given in terms of bias and variance, but if it has to be a consistent estimator, then both of them should go towards 0 as n tends to infinity. So, now let us look at that what are the definitions of bias and variance to take it forward. The bias means, say first of all, let us take that here is the variable theta, if we want to estimate, and if the estimated value is theta hat. Okay. So, in that case, the expected value of theta hat is providing the mean. So, difference of expected value of theta hat minus the true value, it gives us the bias. That means, the mean of the estimates, how far it is from the true value, this is called the bias. Okay. So, if there is any difference all the time, we can say this is the bias, and if someone has the idea that how much would be the bias, you can have a corrections also. For example, for a particular range, if we know your estimates are always higher by say some certain value, so you can apply a correction all the time. We see that when in the market when the vegetable sellers they sell something and their balances are not perfect, they use small weights to balance it. So, that we can call bias, that every time they do the measurement, they know the results will tend to one side, they are trying to compensate it. So, that is a simple example of bias that can be corrected. The next thing is variance. The variance we already know, it gives us the spread of that estimated result from the true value. Okay. Here we have taken actually the difference from the true value, assuming that it is going to give us the bias is going to 0. Otherwise, you can actually write it the difference between theta hat minus theta bar square and expectation of that, where theta bar is expectation of the estimates, the mean of the estimates. Okay. Here we have assumed that it is 0 mean. So, we have directly written it as theta. Okay. Otherwise, we should have written it in this way. Okay. So, we get the expression of bias and variance, and now let us look at that our working definition of the periodogram using the sequence x n for n varying from 0 to capital N minus 1. Okay. From this definition, now we will try to find out that how the bias and the variances they come up. Okay. So, first we will look at the bias. The periodogram we can actually get as a identical to the Fourier transform of the estimated autocorrelation sequence. Please note this term. It is not the ideal autocorrelation sequence, but estimated autocorrelation sequence. We have already shown these things earlier. We have shown that previous derivations starting from the value that we have, that starting from the original definition of PSD, and from there that we have derived, we got that for that case it is going towards that the PSD with ideal autocorrelation sequence. But here the things are little different. We do not have that n tends to infinity here in this case. Expectation operator is also dropped. So, we are getting actually we have to be contented only with the estimated autocorrelation sequence. Okay. And that estimated sequence is given here, that what would be the autocorrelation estimate here. However, what we find, this is a biased estimate. Why it is biased? Because we see as the lag increases, that means the value of k increases, the sum within this summation term it decreases. It does not remain to be same, whereas this term of scaling that remains to be constant 1 by n. Okay. So, we do not get actually the real value. So, if we now take the expected value of that periodogram which is required to calculate the bias, then we get that expectation operator will work on this estimated autocorrelation sequence. So, now let us look further that what we get out of it. As we take the expectation, for that we can replace this one with the real value. In fact, what all we are doing, we are making use of this expression of that autocorrelation estimate, and if we take the expectation of it, we are just counting that here within this summation, this term will give us the real autocorrelation function if we take the expectation. Now, how many times that will be repeated, that will get by this term. Okay. So, taking them together, we get this expression which would be maximum at the 0th lag, and it will get tapered down as it is going increasing value of k. Okay. So, what we get here, we get a new function like this, which is present along with the original expected value, that is the autocorrelation and that Fourier kernel, which should give us the estimate of the frequency. Along with that, we have a new function, and that function, if we tell, that is WB, it is a windowing function or weighting function applied on the autocorrelation estimate. Then we can tell that here we are computing the Fourier transform of the product of the window or weighting function multiplied by the autocorrelation of the signal. So, that much we can get from here, where WB, it has a particular form, and with the help of that we can actually write in the frequency domain from this term, that this term from the Fourier transform, when we have the product of the two terms, they become convolution in the frequency domain. So, that gives rise to this, the next line, where we get that it is convolution between the function WB and the PSD, that is the Fourier transform of the autocorrelation function. That convolution is occurring in the frequency domain, where this WB is the Fourier transform of a triangular function, which is also known as Bartlett window. So, we get something that what we were looking for, we are getting not exactly that it is not giving us the PSD, but PSD, the original PSD, which is convolved with a window function. So, actually we can say a bit corrupted form of the original thing, but somewhat close to that. It depends on how this function would be. Okay. So, this triangular or Bartlett window, we can look more carefully. It is a window which is having the highest value at 0, and it is when it is becoming actually linearly, it is decreasing in both the sides, it is symmetric, and beyond the value n it will become 0 in both the sides. Okay. So, it is a triangular window, and the frequency transform of it comes in the form of a sinc function, okay, which would be centered at 0. So, this means our parallelogram, it is a convolution of the true PSD with the Fourier transform of Bartlett window, and what convolution gives us is gives us a smeared view. In a positive way to look at it is giving us a smooth version. Okay. If you are very picky, then you will tell that the details of the spectrum is lost. If you look it in a positive way, then you will tell the roughness of the spectrum is removed. So, we are getting a smooth version of the true PSD. Now, if the PSD is a continuous one, say it is like this, then smoothing will not probably make much change, but if you think if it is a monotone signal, so it is like this, single frequency is present, then after this convolution it will give us value like this, the output would be like this. Okay. So, in essence what we get out of it, that parallelogram is a biased estimate for finite set of data, but unbiased as n tends to infinity. As we have seen previously, that parallelogram is giving us the windowed result or convolved with a Bartlett window in the PSD, but benefit is that if n is large and it tends to infinity, this triangular function it will change, and ultimately that the frequency transform of this Bartlett window it will converge towards the impulse response. So, we should get a unbiased estimate for infinite amount of data. So, starting from that point that we told that if we have infinite amount of data, whether parallelogram will give us that consistent estimate or our results will converge to the true value, the answer so far is no if the data is finite, but it is yes if it is infinite amount of data is present. So, so far we can tell about the bias, that means bias will go to 0. So, that is again a very good positive result. So, with that in mind, we go forward to see that what happens to the variance. So, for that we look at the second order moment of the periodogram. That second order moment or covariance at two frequencies f1 and f2, if we take, it is given by a bit complicated expression given here, because each of these term it involves actually two sample terms. So, here we have 4 terms of x and thereby having 4 indices of summation, and in the same way that we have 4 indices in the exponential term also. Okay. So, it becomes a little more complicated and we are unable to actually evaluate it in a general form. We cannot take it forward in that way. So, we take a easier route, we take a very specific example where we can deal with it. If we take x n is white, if x n is a white noise, then this expression becomes much more simple and tractable. In that case, that we get this most complicated term, that is expectation of these 4 terms. It gives us actually product of some delta functions which can be given in a simpler way, that this is equal to sigma to the power 4 when k equal to L and m equal to n, or k equal to m and L equal to n, or k equal to n and L equal to m. All the other places it would be 0. So, we could get somewhat tractable value of this, and using that now we will see that how we get the second order moment. Now, using that we get this expression for the white noise. Okay. So, we get the 2 terms at 2 different frequencies, we can say the sinc functions we could get. And now, using this we can write the covariance what we are looking at. Covariance is nothing but the term what we have taken, the expectation of the 2 terms minus expected product of the expectation of each of these terms. Now, this one we already know that it would be sigma to the power 4. We get rid of this term. So, we are left with this expression. Okay. Now, this is somewhat simple, at least we could get some form, but it is not so simple that we could be very contented about it. So, let us look at now the case of variance, what happens. For the variance, we have f1 equal to f2 equal to f. So, in that case, out of the 2 terms, sinc terms, one will vanish, where we had the term f1 minus f2 and the other term that f1 plus f2 will give rise to this expression. Okay. So, the first observation is variance is a constant independent of n. Now, this is however, is not a very good news. We were expecting as n tends to infinity that variance should come to 0, but because of the presence of this term we cannot say that n is actually affecting this variance and it is going to 0. Okay. So, what we get, periodogram is a unreliable estimator, as the standard deviation is as big as mean. Why it is so? We know that the first term, if you look at, this is the actually the mean Pxxf is the true value. So, what essentially we are telling that whatever the mean value is there, variance is as much as that. So, that immediately gives us that view that whatever we are getting out of periodogram, it has lots of fluctuations and the values we get, that is very much unreliable. And at this moment you may doubt my words that what sir is suggesting, how that can be true, what we are teaching in a class. All of us, we are very confident, we take the Fourier transform, take the absolute value and we comment on the frequency content of the signal. I think all of you have done that at some point of time. Please take some simulation environment, whatever you are comfortable with. It may be MATLAB, it may be Scilab, it may be any other tool. Take a random sequence, rather to be more precise, it would be a pseudo random sequence you take data from 0 to n minus 1, take little large value so that you get a good estimate, compute the Fourier transform of that white noise and you take then the absolute value of it and plot it in front of you. Look at the plot. What you are expected for a white noise in the frequency domain, it should give us all the frequencies at the equal magnitude, but you will find plot looks like this. It not at all a constant value. That is because you have used periodogram and periodogram is not a reliable estimate. After doing this experiment, I hope that you would be convinced about what we are teaching in this class, that it is not reliable because the variance is as big as the mean. Now, variance at a given frequency, we know the expression. Now, we look at that why such fluctuations are happening. Let us take some frequencies f1 and f2. which are harmonics given by m by n and small n by capital N. Okay. So, you get that these are the actually frequencies what you typically get when you take a DFT, that the DFT values you get in this way. So, where m and n are distinct integers in the interval minus n by 2 to n by 2 minus 1 for n is even, and minus n plus 1 by 2 to n minus 1 by 2 for odd value, and it results in 0 covariance. How do we get that? For that we have to go a little backward. We have to look at the expression of the covariance once more. In the covariance one, we got the two terms here, that now here if we replace f1 is the first term, that numerator we are taking sine of n pi, f1 is say m by capital N, the other one is small n by capital N. So, we can write sine of pi into m plus n. M and n both are integer. So, this is equal to sine pi, which is 0. Same is true for this one. There you will get the expression m minus n would replace actually m plus n. This term would be replaced by m minus n, because we will have here minus. So, again when m and n they are integer and different, it will be same as sine pi. So, it is a very easy derivation. We could get that the values of the covariance would be 0. So, from there we have to accept that fact that two frequencies, if we take harmonic frequencies, the covariance would be 0. So, the values of the periodogram separated by an integer multiple of 1 by n are uncorrelated. If the covariance is 0, that means they are uncorrelated. Now, you get that why we would expect to get random noise kind of pattern instead of a constant frequency or a constant value of the signal energy for PSD when we take the Fourier transform of white noise and look at the absolute value of the Fourier transform. Okay. Because the values are uncorrelated and they have high variance. So, we are getting instead of constant value somewhat uncorrelated values, which looks like random noise, and truly they are expected to be so, because we have taken periodogram as an estimator. So, here few more small features we would look at. So, what we are expected to get, that we will get rapidly fluctuating periodogram. Okay. So, instead of getting better and better estimate as we expected with the signal length, we expected the bias is going to 0. So, we would get more and more close to the true value Instead of that, what is happening? We get periodogram becomes more and more rough, it is becoming more with fluctuations. Okay. So, that is the benefit we are getting with length of data or increase in data. And in some cases it can be really difficult, especially when we are looking for sinusoids or narrowband signals embedded in white noise. One such application comes immediately in our mind, that is the radar application, where we inject a frequency and look for that the returning waves, and those sinusoids, they could change the frequency because of the Doppler shift, but the change would be very small. So, that the wave that is getting reflected from a stationary barrier, it would have the same frequency as the transmitted wave, and for a moving target it will give a little different frequency. But so, two sinusoids, two actually frequencies we are supposed to get, or two impulses we are supposed to get, which would be close by, and white noise is there, which are having fluctuations. So, what can happen? These two may get merged because of these fluctuations. So, you would not get that there is a moving target. Okay. So, in this case, that the data windowing becomes very important to reduce the side lobe. Okay. So, that is one of the thing we realize, that if we have to use periodogram, we need to use some kind of windowing. Without that, we cannot go ahead, and this windowing is just to take care of this rapidly fluctuating periodogram. So, earlier we are trying to get rid of that, wanted to go for ideal case by increasing the data. Yes, by increasing the data we have more information, but because of these fluctuations we need to go for some windowing to reduce the side lobe frequencies, so that those peaks does not get actually merged. Okay. So, we can look at different kind of windows, and Hamming window is one of them, which gives good reduction in the side lobe. It gives up to 40 dB or more, but it comes at the cost of the main lobe bandwidth. Okay. We will leave it here, we will come back after a break. Thank you.